Hey, Gerald?
Gerald?
I haven't seen him anywhere around here.
Oh, he's not downstairs anywhere.
The mills were taping today.
I hope so. Hey, Gerald? Gerald, you up here?
Yeah,
Where you at?
I'm in the tub. Who are you?
Tub? What are you doing in there?
What are you guys doing here?
We're supposed to be taping today.
We're taping tomorrow.
It's today.
Are you taping right now?
That's right.
All right, listen. Excuse me if I don't stand up, you know? Give me a few seconds to kind of compose myself. Why don't you cut to the opening montage? I'll come back and I'll say something about a bathtub or something like that. Just give me a few minutes anyway.
The Kinetic Karnival, energized by Dr. Joel Walker, professor of physics, columnist for Scientific American, and author of the book, Flying Circus of Physics with Answers.
There's an old tale about bathtubs, the way they drain. In the Northern Hemisphere, they drain out counterclockwise, and in the Southern Hemisphere, clockwise. Is that true? Well, even if it's true, why should there be any kind of preferential direction for draining? Well, to make sense of this, I have to make you take kind of a spaceman's point of view of the Earth. The Earth is truly rotating around an axis that goes from the North Pole to the South Pole. A piece of Texas has to go around a rather large circle around that axis, does it in 24 hours, so it has to go at a pretty good clip. A piece of Canada goes around in a much smaller circle, so it has to go around a little bit slower to make the trip in 24 hours. Now, here's a silly example. I know it's silly, but I have to make the point on the physics. I'll have a friend, I'll be in Texas, I'll have a friend in Canada throw a baseball to me, and the baseball will come all the way to Texas. And my friend's going to throw it due south as best he possibly can. But what I want you to imagine is what you will see from your spaceman's point of view. You see the ball come south, but it's also traveling around the axis of the Earth with whatever speed my Canadian friend was traveling around. The baseball comes south. What you will see is that Texas will be going around the axis much faster than the baseball. So by the time the baseball gets to Texas, that low down, Texas is pulled ahead of the baseball. Well, what am I going to say about this from my Texas point of view? I see this ball coming due south from my friend, and it mysteriously deflects. From the baseball's point of view, it will deflect to the right. It might end up in West Texas or New Mexico or something like that. How do I make sense of that? I say that there was a force on the baseball during its flight that caused a deflection. We call that force a Coriolis force. There really isn't any such force like that. And you know that from your spaceman's point of view. You know that Texas went around the axis of rotation a little bit faster than the baseball did, that's all. But from my Texas point of view, I don't understand that image. And I say, hey, there was this force acting on the baseball, the Coriolis force. Well, you really don't see it with baseballs in the everyday world because the baseballs just don't travel that far. You might see it with artillery shells fired over a long distance. And sometimes that's a real problem during a war when you're pumping artillery shells for a long distance. The best place you could see it, this Coriolis effect, this force, this mysterious deflection, is with large-scale wind systems, such as when a hurricane is developing. In a hurricane, in the Northern Hemisphere, wind will blow from a high-pressure region into a central low-pressure region, blowing in. And as the wind comes in, it deflects to the right. I don't care which way it was going, it will always deflect to the right. So as the winds head into this low pressure region, it starts to swirl around in a counterclockwise direction. You now have a hurricane. In the southern hemisphere, if you've got a hurricane developing, the Coriolis effect, the force, that mysterious deflection is to the left. And so as the winds head from the high pressure region into the low pressure region, they all deflect to the left. They end up swirling clockwise in a hurricane in the southern hemisphere. Wonder if a hurricane in the northern hemisphere crossed the equator into the southern hemisphere, would the Coriolis effect cause it to reverse its swirl? No. The Coriolis force is so tiny, so small, that once the hurricane has developed, it's got so much mass and so much energy, it's so violent, that as it slips across the equator, the little feeble Coriolis force is going to be insignificant to cause a reversal. Well, you see the Coriolis force, this mysterious deflection, with hurricanes all the time. You don't see it with smaller scale wind systems, like a tornado. Tornado, the wind doesn't go very far, and it's so violent that this tiny little force has no control over it. How about a bathtub? It would be a lot of fun if I could show you the Coriolis force, this deflection, here in the bathtub, but I cannot. When I pour the water into the bathtub, the turbulence that I'm putting into the water is so severe that it swamps out the Coriolis force when I drain the water from the bathtub. In fact, the asymmetry of the bathtub is going to overwhelm the Coriolis force. My pulling the plug, little bit of disturbance that it is, it's still too much. It'll swamp out the Coriolis force. If you really want to show the Coriolis force in a bathtub, you have to go to the trouble of making a nice, symmetric, circular bathtub. Put the water in, let the water sit for a day or two, something like that, to get rid of all the turbulence, and then very, very carefully pull the plug so you have just a little bit of disturbance there. Then as the water starts to drain from the tub, you might be able to see the counterclockwise rotation that's supposed to take place here in the Northern Hemisphere. Chances are, if you go to 1,000 normal bathtubs, take a little survey, interrupt people while they're taking their baths or something like that, you'll find that about half the bathtubs have swirls one way, about half the bathtubs have swirls the other way. You might even, like with my own bathtub, find that the swirl reverses itself during the draining. It might start out counterclockwise, but then midway or so during the draining, it might switch to clockwise, and then it might even switch back again. All that's determined by my splish-splashing around in the bathtub, by the turbulence in the water. When I first put the water in, it certainly hasn't died out yet, by my pulling the plug, and by the general shape of the bathtub. We'd have to go to a lot of trouble to finally see the Coriolis effect that's in that old tale about bathtubs.
Well, it's too bad that the circulation doesn't work out in the bathtub like the old wives' tale would have it, or I think bathing would be a lot more fun. Today I'm going to show you a few other circulating systems, talk a little bit about fluid flow and about friction, and how fluid might play a role with the friction, in lubrication at least. Sometimes it does, sometimes it doesn't. One of the strangest circulating systems I ever came across was when I went to a gypsy's tent. I like going to a gypsy's tent a lot. It's a lot of fun. She was going to tell my fortune from the tea leaves, and so she put some tea leaves in a cup. I'm going to use a bowl just so we can get a better shot of this. And then she poured the water in, a little bit of water. And then, just so she could tell what I'm going to be doing for the next 10 or 15 years of my life, she stirred the tea leaves around. And she saw remarkable things about my personal life and stuff like that. And the tea leaves, I looked, I didn't see anything. But I did notice that when she was swirling the tea leaves around, swirling the water, that the tea leaves did something very wrong. If you go around in a circle, you're thrown away from the center of the circle by what is called centrifugal force. Tea leaves should be thrown outward from the center by the same force, and yet they all collect at the center, except for maybe the ones floating on the top. The rest go right to the bottom and to the center. How come they do exactly the wrong thing? It's because when she was swirling that water around, not only was she swirling it in circular motion, but she was also setting up what is called secondary flow. Let me see if I can make sense with that kind of idea. Once you get the swirling going, there are pressures set up inside the fluid. In dead center, relatively low pressure. Out toward the wall, higher pressure. If you were a little piece of water, you would try to be pushed from the wall to the center. Well, it turns out that on the bottom, next to the bottom, because the fluid has to rub against the bottom, there's less pressure difference between the center and out near the wall. There's greater pressure difference between center and out near the wall on the top surface. So if you're a little piece of water, let's say you're at the top next to the wall, you're going to be pushed down the wall by the pressure difference between top and bottom, and once you reach the bottom, you're pushed toward the center, and somebody's going to have to take your place because of this movement on your part. So other pieces of water come up the center, go out toward the wall. There is a circulation that you don't normally notice. It's called secondary flow. Circulation is from outside wall, down along the wall, toward the center, up the center, out to the wall again. Well, when the water goes along the bottom toward the center, picks up the tea leaves, and then deposits them at the center when the water starts to go up through the center. And so you get that collection of tea leaves in dead center. Well, that's kind of fun. I'll show you another one. You can see if it's kind of a bright morning or bright evening, make myself a little cup of coffee here. I like my coffee really strong because that's the way real men drink it. And put some hot water in here. You have to have the light just right to see this circulation system. Whoops, almost just overpoured it there. Once the swirling dies out here, if you look carefully with the light just glancing off the top, you'll see a rather pretty circulation pattern develop. It's starting to develop. If you look just right, you'll see whitish areas outlined with black lines. What's happening is that the water in the coffee is cooling at the top surface because of evaporation. Cooler water is more dense than hotter water. So once the water on the top surface cools, it has to descend, and it's replaced by hotter water. Comes up from the bottom. You could accomplish the same thing if you had this on a stove and you were heating the bottom. All you need is hotter layer down below, cooler layer up above, and you start getting these little patterns. Well, the hot water rises, and as it hits the surface, it sprays up some tiny little drops. As the light glances off those tiny little drops, it gives a whitish appearance to the surface of the coffee. The coffee itself is black, but the little drops will give you a nice reflection, looks whitish there. In the regions, kind of narrow regions, where the water is descending because it's cooled, there's no little drops up above the coffee, and so that area looks black, like coffee should look black. And the pattern is not very uniform. It kind of swirls around majestically. If you're really lucky, you might occasionally see a little whirlwind dash across the top, momentarily destroying that pattern that the circulation, the hot and cold liquids set up. Well, that's kind of nice. I think I'll wait till later to drink this. I noticed one other. Well, this was kind of an embarrassing fluid flow example. When I was younger, I really had a crush on a girl named Marcia, and had my first date with her, and I was just starting to drink beer and thought I'd kind of impress her about how masculine I was, drinking beer and stuff like that. So I had a beer, kind of like this one, and I thought I would look her straight in the eye, romantic eyes, and I would say sweet nothings in her ear. And I would just pour the beer kind of suave-like into the glass. And the thing that I didn't count on is that when you pour the beer into the glass, if you're not careful and pour very quickly, if you just kind of pour slowly, as I was trying to do, that the beer comes running back along the bottle and ran onto my shoes and onto my pants. And she thought I was real neat. Had wet pants and shoes there. I could pour the beer so well. How come the beer runs around the lip and then kind of hugs the beer bottle to run back and onto pants and shoes and stuff like that. I mean, this happens with most fluids unless you take some really good precautions. Pouring it fast will eliminate the problem, but if you pour slowly, it goes right back like that. When the beer, or whatever liquid you've got, comes out and goes around this rather sharp edge, it speeds up. And according to what is called the Bernoulli principle in physics, when you have a fluid speed up like that, the pressure in that fluid decreases. As a matter of fact, once the fluid comes around that sharp neck there, it's about to be poured, the pressure in it decreases enough that the air pressure outside the stream is actually more. And so the air pressure pushing against the stream holds the stream to the beer bottle and brings it along the edge until finally it grows unstable enough that it just kind of drips down like that. Well, it's probably enough for my pants anyway. But sometimes fluids can help you. Sometimes they can be kind of embarrassing like that. Probably one of the worst examples of a fluid flow. It's disastrous. You're driving along in your car late one night, raining like mad, and all of a sudden you see a giant antelope jump out in front of your car, and you know you're going to have to stop the car very quickly, so you slam on the brakes. But it's been raining, so you start to slide down the road. You're sliding because you've got virtually no friction left between the bottom of your tire and the road surface. You're sliding on a thin layer of water. You're hydroplaning or aquaplaning, two words for that effect, and you've got virtually no friction left. The modern design on the tires is meant to take the water layer beneath the tire and throw it to the rear of the tire, so you can kind of eliminate or at least reduce that water layer that's going to prove disastrous as you slam into the animal in the road there. Well, it doesn't work too well. You can hydroplane even with the best of tires these days. You need that friction if you're going to stop quickly. Let me explain to you what friction is. Here's a beer bottle. There's no friction at all in this beer bottle right now. It's unmolested, just sitting there nicely, waiting to be drunk. No friction at all. But if I push slightly on the side, I create friction. I'm not moving the beer bottle now because the friction exactly opposes my small push to the side. How come? Well, the bottom of the beer bottle may look pretty smooth. The tabletop may look pretty smooth, but neither are very smooth on a microscopic level. It's crammed with hills and valleys. Well, if the beer bottle is just sitting there unmolested, those hills and valleys kind of mesh into each other. There's no friction. If I push on the side a little bit, I cause the hills of the beer bottle to cram into the hills of the tabletop. That's the friction, that cramming together of the hills. And there's just enough friction to oppose my sideways push. Well, I can push a little bit faster or a little bit harder, and still the friction is just enough to oppose me. I'm cramming those hills together just a little bit more. I can keep playing this game only up to a certain point. Finally, I'm pushing just hard enough that the bottle's on the verge of sliding. Now, the friction up to that point is called static friction because there's no motion involved between the two surfaces. But the bottle is now on the verge of slipping. The greatest the friction can be is there just then. If I cause the bottle to slide, the friction is suddenly reduced. That friction is called kinetic friction, sliding friction, dynamic friction. There's lots of names for it. But the point is that once you go into the sliding situation, the friction drops in value. You don't get as much friction. Well, how come? There could be several different reasons depending on the circumstances. I might cause the hilltops of the two surfaces to shear each other off, so they won't offer as much resistance. That might be happening here a little bit, removing a little bit of the wood or a little bit of the glass, probably not too much. I might cause the two surfaces to hop along together, and there wouldn't be quite as much friction then. But more disastrously, or maybe even some more fun, depending on what you're doing, you could actually melt the two surfaces because of the heat, that rubbing together. I mean, I first noticed this when I was a lot younger, and I thought it was really neat to suddenly slam on my brakes and go sliding down the road to scare people and stuff like that, and terrific squeal, and you leave these tire marks down the street. The tire marks are is the melted rubber from the heating between the tire and the road surface. Once you lock your wheels, you melt some of that stuff, and you go sliding because you've got a layer of fluid between the tire and the road surface. It acts as a lubricant, so you slide on that lubrication. Well, I also like to kind of drag race sometimes in my mom's car. I'd stop the car and shift it into neutral and gun the motor and shift it into drive and slam out, and thought the squeal was really quite masculine. Everybody would be real impressed. And I'd leave these terrific tire marks on the street, impress everybody. That was the melted rubber from when I slipped the tire over the pavement surface. You might see something like this in a real dragster situation. You got the funny cars at the track. They're about to switch on the green light. You're gunning your motor like mad. You're ready to dash down the strip, the quarter mile. Well, it would be kind of dumb if you suddenly engaged your wheels and all your wheels did was spin around like that, and the other guy would be all the way down the track by then. So what they try to do is put sticky stuff between the tire and the pavement there to keep the tires from slipping so that they get more friction. They don't want to go into the sliding situation because that automatically reduces the friction, and they would just spin there, not going anywhere. Probably an even prettier example of lubrication is if you're ice skating. Ice skating, long, gliding gracefully over the ice. What you're really doing is moving over a thin layer of water. Your weight, that pressure on the thin blade that you're standing on, melts the ice right beneath the blade. That's the lubricating fluid. You're not gliding over solid ice, but over liquid water. You cannot ice skate on really cold days because your pressure on such cold days would be insufficient to melt the water beneath the blade so that you can glide over it. You could go out, put on your skates, and try to skate, and you just fall on your face and everybody laughs at you. It's not much fun without that lubrication. I have another example of the difference between static friction and dynamic friction. Here is, well, it's my only set of dishes, as a matter of fact. I brought them. I'm a little bit hesitant about doing this because I'm not real sure it's going to work. I used to have more dishes, but practicing for the show, I ran out of dishes. I'm going to try and pull this tablecloth from beneath the set of dishes, and I bet you've seen this before and thought there was some trick involved. There's not really any subtle trick, just a little bit of good physics. When I pull the tablecloth, well, if I pulled kind of slowly, the only thing would happen is I'd pull everything toward me, and if I were foolish enough, I'd pull it all into the floor and make a big mess. If I pulled a little bit harder, I probably wouldn't accomplish anything but to bring the dishes toward me even faster. What I've got to do is pull really hard and really uniform and put this tablecloth and the bottom of the dishes into a sliding situation very quickly. And if I can do that, I reduce the amount of friction between the bottom of the plate and the tablecloth, and the tablecloth just pulls gracefully from beneath the set of dishes. Okay, try this. Actually, the first time I did this, I was at my grandmother's house, a little bit younger, and I explained to her about all this physics about kinetic friction and static friction and stuff like that, and I dropped my voice so I sounded like a professor, and I really knew what I was doing. And I insisted on showing her that it would really work, and I used her 50-euro set of dishes, and it was very elaborate and crystalware and stuff like that. Dropped the entire thing into the floor. She didn't speak to me for a month, and she knew how much my physics was worth then. Okay, try it here. Pull very quickly, very uniformly, and tablecloth slides from beneath the plate and the cups here, you know, because the friction will be immediately reduced, and it won't be as much friction then, and everything will just slide right underneath, and the plates and the cups will still be there, and they won't go into the floor at all. I mean, they got pulled very quickly, very uniformly. and my grandmother were here. Well, since that worked, let me get a little bit braver. Nice tablecloth, dishes back, little setting for two. Should have some candles here, a little bit of wine. Put a little bit more wine in here. Now, I'm not sure this is going to work because, whoops, spilled a little bit of wine. Uh-oh. Because these wine glasses are a little bit unstable, but I'll try it. You don't mind having a little bit of wine on your lap. Goodness knows I've had wine on my lap many a time. Okay, very quickly, very uniformly, tablecloth, slide right beneath plates and wine glass and without spilling a single drop. Have to pull very quickly though. If you pull very slowly, it just... Okay, here we go. Usually think of a fluid as being a lubricant, but it doesn't always work out that way. I'll show you a little dinner time treat when the party's kind of growing a little bit dull and you want to kind of spice it up. Take a spoon, you kind of clean it off on your shirt, which right away is kind of disgusting. And you clean off your nose, which draws even more attention to yourself. And breathe very lightly into the spoon. Just get a little bit of condensation there. Then you hang the spoon from your nose. Now, how come the spoon will hang like that? Because, you know, water is a lubricant. Well, I put a little bit of water between the spoon and my nose, and yet the spoon's not sliding off my nose. I know it looks real cute. I actually went through 6 years of graduate school just to learn how to do this so I can come on TV and hang a spoon in such a fashion. Water, if it's thick enough, acts as a lubricant, but you have to have enough water so that one layer of water will slide over another layer. Then you get the lubrication. But if you have a very, very thin layer of water, just a few molecules thick, then you get adhesion. The water molecules will adhere to the spoon and to my nose, and so the spoon is effectively stuck to my nose. So water doesn't always act like a lubrication, like you would think. Now, if you're really into heavy masculine things to do, you try a big spoon. I think I'm masculine enough to do this today. A little bit of condensation there, and then I reach up here. Whoops. Well, not quite that masculine today. I clean off my nose. I know I can do this. And there it is. And you can see just how terribly masculine I am. And, yeah. I actually discovered this effect while sitting in a French restaurant, and I decided to see how long I could hang a spoon from my nose. My record is 1 hour and 45 minutes. The restaurant owner asked me to leave and to never come back again, but I did set the world's record for the time of hanging a spoon. I'd like to have a national contest on hanging spoons. It would be called the Spoonhead Contest. People holding local contests, hanging spoons from their nose or something like that. Okay, gang, I want everybody to try and hang a spoon from your nose. Everybody's hanging a spoon? Well, that's it for Kinetic Karnival today. Another little thrilling example of physics in action. Hanging spoons from your nose.